Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight.
Has it already been 2 weeks? That means it's time for another scientific chat, hot off the heels of the Mediterranean Sea disappearing. We're heading back into the cosmos. Whimsical wavelengths is where we answer, why did the astronomer break up with their favorite star? Well, it's because the relationship redshifted too far away. When it comes to the cosmic science, we've covered gravitational lensing and novae, the proper plural of nova, which we will come back to after TCRB, or the Blaze Star, finally puts on its show. And yes, this was originally covered with my uncle, Dr. David Zurich, in episode 4. Dr. Gorgos Vanados took us on a journey to understanding some of the important parts of gravitational lensing. If this episode leads to a want or a need of a full discussion of relativity or gravity, please check it out. Today will definitely still include gravity, as I have a guest to tackle galaxy formation and evolution. There is so much we don't understand about the early universe, or really any part of the universe not nearby. Part of the reason for this is time and distance. The universe, as we understand it, or see it today, started 13.8 billion years ago, or thereabouts. And I should caveat that there could be something before this time, we just have no information. The Big Bang is the event that started the universe, or at least the visible universe as we understand it today. In that beginning, the universe was like a hot soup of particles. Protons, neutrons, and electrons eventually came out of it. As it began to cool and expand, energy turned into matter. And eventually, that matter became hydrogen and eventually some helium. As matter concentrated, it formed the first stars and galaxies. Well, that's the broad 10,000 meter elevation view I have of all this whole affair. We know what we know because of our understanding of physics and relativity. Yes, there's that name again. The cosmic background radiation and observations back in time as we look further and further away, because light travels and it takes time for it to travel. So why don't cosmic rays ever get invited to parties? Because they always cause such a big reaction. So how do we test something that we cannot view? The evolution of galaxies takes place over billions of years. So we're only around for a short period of time. We as individuals cannot track its changes over eons. Remember, human history is in the thousands of years. So, and only the observations we have cover maybe decades? Yes, we can see many snapshots of different galaxies at different points in their evolution, but how can we connect all of them on their journey? One way is to model physics or physical processes, put everything we understand into one mathematical framework, run the code or the model, and see if it matches what we see in our observations. We do this type of exercise with many different scientific disciplines, including my own, geophysics. Time to bring in this episode's guests. Please welcome Eric Andersson, a postdoctoral researcher at the Museum of Natural History in New York. Got his PhD in MSc and BSc from Lund University, PhD in 2022. Currently, he works with developing numerical models of the formation and evolution of galaxies. Welcome.
Thank you so much for having me. I'm very excited to be here to talk about stars and galaxies.
Awesome. And to be frank, I'm absolutely ecstatic that you're here. And I'm going to start off with a repeat question. And it's also very interesting always about trying to get that first couple of sentences of someone's research. So with minimal jargon and complexity, what are your primary research questions?
So broadly, I want to understand how stars form, interact with their surroundings, and ultimately shapes galaxies over time. And evolution in time, I think, is a key part of this question. So a large part of the work that I do revolves around developing numerical models that we can use in simulations to let us view a process that happens across billions of years in a sense that gives us an understanding of the time evolution, because this is very hard to get when we observe galaxies with telescopes.
Yeah, and I think we'll get back to the whole time thing, because billions of years is something most of us have really hard time wrapping our heads around. It also seems like your degrees were a bit of a straight shot from BSc, your bachelor's, right up to your PhD. So was astrophysics and cosmology something that really grabbed your attention really early on?
I think so. So when I grew up, I have a father who's very interested in stargazing and astrophotography. So when I was a kid, me and my brothers usually, or my father usually showed things that were interesting in the sky with his telescope. So I think that's very early on that probably gave him an interest in astrophysics. But I would say before I went to university, it wasn't such a straight shot into academia. I actually started off working in carpentry for a couple of years before I went into academia. And around, I think, I'd say this is probably, this is around 2012. I decided to basically take a year off to study science, because this was something that I did have an interest in, but it was more natural science in general. So I studied this for a year, and I realized that mathematics and physics was for sure the things that interested me the most. So one thing led to another, and I started a bachelor's degree in theoretical physics. And after this, I did a master's also at Lund University. And after this, I just kept going, and I got a PhD in 2022. And yeah, I'd say the common theme for all my research has been to involve numerical simulations one way or another, though.
So you dipped your toe into the dark side and was sucked in.
Exactly.
Okay, so let's get towards the technical side of things. Galaxies are made up of many stars. So presumably we need stars before we can have and form a galaxy. So why don't we begin our journey of technical questions on how stars form?
Sure. So let's start simply. Let's imagine star formation as a process. So we think of a cloud of interstellar gas somewhere in the universe, and this cloud will collapse under gravity and eventually form stars. Now, there's a few key things here that we need to keep in mind. First of all, this cloud of gas that we're imagining, it has some temperature, and this temperature has to go away for gravity to win and then get to the star formation process. So part of this process, and something that's very important, is cooling of this gas. So this is something I think we'll come back to. But broadly, when we think of stars forming, we take a cloud of gas and we let that collapse under gravitational forces. And the way that counteracts this compression is basically the thermal pressure or the temperature of this gas. So it's a competition between gravity and thermal physics.
So the expansion of the gas under higher temperature can fight gravity and stop a star from forming.
Yeah, and basically what lets gravity win in the end is the fact that this gas will be cooling.
So how do we meet the two there? You need a certain density and temperature to eventually hit fusion, right?
Yeah, exactly. So that's basically when we're at that scale, when it's dense enough to trigger fusion, that's when we call this ball of gas stars. One very important thing to keep in mind about this process when stars form is that when you have a gas cloud and that's collapsing to form stars, it basically never happens that we get a single star. Stars tend to form in groups or clusters, and that's one of the key things to keep in mind, that stars don't form alone, but they are born out of gas clouds in the form of groups and clusters. So when we talk about star formation, or we typically talk about the formation of populations of stars. So things like mass distributions of stars becomes important.
So I guess a slight deviation, we would have had for our own sun other stars forming nearby. Do we know which stars those are, or that so far in the past they're just kind of elsewhere in the Milky Way?
It's very hard to know exactly what stars the sun was born together with. we can get indications. So one of the things that can tell us whether stars form together or not is the chemical composition that makes up the star. And this is something that we can measure. So we measure this in the sun, and we determine the amount of specific elements in the sun. And then we can look for stars that resemble that chemical composition. And then we can get an indication that these stars form together. But it's very hard to tell exactly what stars form together with the sun. But
Because of the time difference, I would imagine. They've all kind of gone in different directions, more or less.
Exactly. So if we find stars that look very similar to the sun, we typically call these solar twins, for example, if we want to introduce some jargon.
Okay, so with stars, we get galaxies somehow. There must be something that happens there. What is that like, or how do we currently understand that process?
Yeah, so let's start by just defining what we talk about when we're talking about galaxies. So basically, a galaxy is a collection of gas, dust, stars, and dark matter. And the way that they form is by concentrating matter through gravitational forces until you reach dense enough environments such that gravity can overcome this thermal pressure that I mentioned before, and then collapse and form stars. And then you have something like a population of stars in a group, and if that group is large enough, then we refer to that as a galaxy. And here is also things like dark matter and gas and dust comes into play. And then this system or this galaxy will assemble more mass, and you will trigger more star formation events. So we have repeated star formation happening in this system, so that it grows up through that in that way. At the same time, we have this happening at different locations in the universe, and these galaxies actually come together quite regularly and merge with each other. So galaxies also grow through a merging process where different galaxies come together, combine to make bigger and bigger galaxies. And one very key thing to understand here is that we typically find that galaxies, or we find that galaxies form in a hierarchical way. And that basically means that we have small structures in the universe that come together to build up larger and larger structures. So if we look at something like the Milky Way, for example, we can tell that this galaxy has been growing up by combining smaller and smaller things. So that's what we call the hierarchical galaxy formation model. And it's one of the key predictions that we have in galaxy formation theory.
Well, we are going to eventually, in billions of years from now, see Andromeda interact with our own galaxy. Is that going to create new different structures, or is it just going to be a bigger galaxy? I mean, the process is the same, but I mean, is there a new term, mega galaxy, like super volcano?
No, that's it's an interesting question. So yeah, as you say, Andromeda and the Milky Way will eventually merge, as far as we can tell, and this will be catastrophic in terms of how the Milky Way looks today. Like, it will severely affect the shape of the galaxy, and it will very likely become a bigger, more puffed up galaxy, and we refer to these galaxies as elliptical galaxies. And right now the Milky Way is a spiral galaxy, so it will kind of transition into a different type of galaxy when this happens.
Okay, so let's start trying to angle towards your set of research here, but I feel we might need a deviation first, because when I was digging across some of the papers and some of the material that you gave me, I came across this phrase: the lowest mass galaxies are star formation quenched during the epoch of reionization. And I have a suspicion we should work through this a bit more to understand that, with the background of galaxy formation kind of set already, that it takes a bunch of stars to form in clusters, gravity collects more mass, eventually you have enough to call them a galaxy, et cetera, et cetera, et cetera. But what does that mean, reionization and then star formation quenching?
Yeah, no, that's a very good point. That sentence is quite technical and it's filled with jargon, but I think we can actually learn quite a lot by understanding what I mean by that sentence. So let's start by just talking about what this epoch of reionization means, because that's a fundamental thing that I think we need to understand. So if we think of the universe as evolving, it goes through different phases. Like we start off with Big Bang, and at this point we have just a hot ball of plasma. This ball of plasma, or the universe, it will expand, and that leads to this gas cooling down. And eventually you reach a state where basically electrons in this plasma can recombine with nuclei. And this is something that happens roughly 380,000 years after the Big Bang. And this is one of the first key things that happens in terms of galaxy evolution. And at this stage, what happens when you take all your electrons and you recombine them with nuclei, the universe becomes transparent, and that means that photons can now travel freely. And this leads to an interesting effect that we call the cosmic microwave background. Basically, you can get a fingerprint of what the radiation looked like when this happened. And we call this the recombination era. And after this point, we basically have a dark universe. So we don't have any stars yet, and the universe is very, very, very young. Then structure starts to collapse. We get star formation. This happens fairly shortly after recombination, actually. And we call this era the cosmic dawn. And when this happens, you start to populate the universe with stars. And these stars will emit radiation. And you can say that you build up like an ambient background of ultraviolet photons. And this keeps going on. And eventually you will see that your entire universe is illuminated by these ultraviolet photons. And at this point, the hydrogen that you have that has formed when neutral hydrogen has formed when electrons has recombined with nuclei, this background ultraviolet radiation starts to knock electrons off these hydrogens again. And we call this reionization. So you're reionizing the gas in the universe. And this is this epoch of reionization that we're talking about. This happens roughly 1 billion years into the evolution of the universe. And it's a very interesting period, because when this reionization happens, we get a fairly well-defined temperature of the gas in the universe, which is around 10,000 Kelvin. So that gives us a well-defined temperature in the universe. And if we now come back to this star formation process that I talked about earlier, and the reason why I mentioned thermal pressure and cooling being important, we now have a temperature for the gas in the universe, which is 10,000 Kelvin. So we can put this into the star formation theory that we had, and we can say, okay, what is the amount of gravity that I need to overcome what is now the average temperature of the universe? And for 10,000 Kelvin, this gives us a well-defined mass for galaxies, or within our approximations. And below this mass, star formation is prevented in these galaxies, and we call this star formation quenching. And it comes as a result of this reionization heating. So yeah, that's kind of what I want to explain with this sentence.
That makes perfect sense. So you can think of it like the Big Bang is afterwards, it's dense, it's hot, it's not going to form stars, and then it starts to cool and you start getting stars, but then you get so many stars that they put off so much, I guess, for the lack of a better word, solar wind, a bunch of ions knock and heat up everything that stops stars from forming.
I would correct you there. It's mostly radiation. It's not really solar wind. It's just high energy photons that is filling up the universe.
While the universe is still relatively small, I'll put that in quotation marks.
Yeah. It's early in the universe, for sure.
Okay. Well, I think that is an important part of understanding the later parts of the questions and your work in general. And I really didn't understand it very well, as you can tell by even after you said it, I still messed it up. But galaxies out there are shining bright like a diamond. kind of like the song, but the research we're focused on today is zooming on something less flashy than the Milky Way or Andromeda. We're talking about dwarf galaxies specifically here. So what makes a dwarf galaxy other than it's smaller? I mean, there must be a definition, like the reason Pluto was demoted to a dwarf planet.
I'm not sure there is a very clear definition of what a dwarf galaxy is. I would say that a dwarf galaxy is a galaxy that has significantly less stars compared to the Milky Way. But when we're talking about galaxies, we typically talk about galaxies in specific mass ranges. For dwarf galaxies in particular, we actually have different types of dwarf galaxies that have more well-defined nomenclature.
Definitions.
Yeah, definitions. For example, we have something called ultra-faint dwarf galaxies. These are the very smallest ones. And we tend to define these as galaxies that has a total luminosity that is less than 100,000 times that of the sun. So then you have a more clear definition of what this is. But for dwarf galaxies in general, I think you have to be more specific what kind of dwarf galaxy you're looking at to have a very clear definition.
Okay, I'm going to make this a two-parter then. So what specifically types of dwarf galaxies do you work with, or do you just work with kind of them all? And is there something about them that makes them better suited for some kinds of study?
I mean, if we come back to this reionization question, like here I said that we have a very specific mass when we don't form stars anymore. And this is actually these galaxies that where this reionization quenching occurs. These are the galaxies that then later on becomes these ultra-faint dwarfs that we observe in the local universe.
And that's just because they didn't have enough mass around them to be able to overcome that temperature. So they formed less stars and therefore were unable to bring together more mass.
Yeah, kind of. Like you can think of it as like, okay, we have this, we think of this galaxy as some kind of potential well. And this potential well is determined by its mass. And then its ability to collect gas that depends on this mass. Then we have this radiation field that heats it up. And you can almost think of the gas being boiled away from this potential well. So we are removing the material we need for star formation. So that stops at early on. And then the galaxy keeps evolving throughout the universe, but it doesn't have more new star formation, let's say. That might change if this galaxy merges with something larger, it grows substantially in mass, then you can re-trigger star formation in this thing, because it might pass the threshold where this reionization quenching is preventing it from forming stars, or reionization heating, I should say.
Okay, so what about, you said there's specific definitions for different types of dwarf galaxies instead of as a catch-all term for dwarf galaxies. So is there particular types that you model versus others?
I mean, it depends on the question I'm asking to some extent. It depends on the process that I'm interested in. I think in my latest publication, I was specifically looking at these ultra-faint dwarfs. And part of the reason for that is because I was interested in studying objects that form stars very early in the universe. So one of the interesting things that happens when you get to this stage where you stop star formation early on is that if you find these things in like the modern universe, or like around the Milky Way today, you can look at them and you can say, okay, I know that the stars that formed in this system formed very early in the universe. So I can study star formation like very, very early on. And then I don't have to deal with all the contamination that would happen from later star formation. So that's kind of why, one of the motivations for why we wanted to simulate this very small galaxy, because it basically lets us in very detailed level look at properties that are set by star formation very early in the universe. It teaches us about early star formation.
That makes a lot of sense. So when I think about simulations, I see them as like testing what we already know. Using climate change as an analogy, we put all the physics, the chemistry, and our current understanding into a model and run it. This allows us to see if we can reproduce what we already know to be true and then run it into the future to see how it changes. For your research, this is the same theme, right? A way to test our current mathematical framework and compare it to the observations we see today.
Yeah, I would definitely say so. That's a big part of it. I think adding to this, like to me at least, one of the very nice things with running simulations, especially for astrophysics, is that we are dealing with things that takes so long. So if you want to study something like the time evolution of the Milky Way, like you can't really see, we only have one snapshot of the history of the Milky Way, right? We can't really go back in time for Milky Way specifically. What we can do is we can look for galaxies that we think are analogs to the Milky Way, for example, and we can say, okay, these are probably what the galaxy looked like in the past, and then we can kind of stitch together some kind of evolution history. But we still have to deal with these snapshots in time.
Yeah, it's not a continuous data set. It's a punctual, separated by millions or billions of years.
Exactly. So that kind of brings another very useful feature of simulations, where we can like make models, or we can try to stitch together these snapshots and kind of get an idea of the time evolution.
Okay, now it's time to get into model parameters. We can build a model that covers all the complexities of the universe, and there are so many stars in a galaxy. The Milky Way has 100 billion stars. Multiple calculations multiplied by 100 billion. Like, how are you able to manage so many stars? Like, there's just so many stars. There must be assumptions to be able to deal with that kind of population, right?
Yeah, for sure. No, it's a hard problem, right? And I guess we're gonna get pretty technical, but
We are. Excellent.
I'll try my best to explain everything. Yeah, as you say, like something like the Milky Way has far too many stars that we can actually simulate, or like we can't simulate every single star in the Milky Way on any of today's computer. It's just too computationally expensive to do this. So one way to deal with this problem, and as I said before, like stars tend to form in groups. They tend to form as populations. So one of the approximations that can be used is to say, okay, let's not think of every single star. Let's just think of stars as groups that form together, and then we're just dealing with these stars in terms of the populations. So now we care about things like the mass function of this population and how that kind of sets how this population interacts with its environment. That's one way to like significantly reduce the number of stars that you have to simulate.
What's significant? Are we talking an order of magnitude, 2 orders of magnitude?
Yeah, many. So it kind of depends on what size do you choose your population to be. Like if you say that, okay, I'm gonna consider stars as populations of 100,000 stars, then we're kind of reducing it by,
5 orders of magnitude.
5 orders of magnitude, right?
5 or 6, yeah.
But that's choice.
For sure.
Yeah.
Okay, but in your particular instance, you're taking on looking at individual stars, being able to look at the individual effects of different processes,
Exactly.
because you're working with dwarf galaxies, I assume. There's less stars to begin with.
Yeah, for sure. That really helps. So one of the recent advances that we've done in galaxy modeling, so like basically when we have this population thing, we've always tried to push the number of stars that we group together as much as possible. But if we keep pushing that down, eventually we will reach a point where it doesn't make sense to look at the stars as a population anymore. Like if you push this mass to, let's just imagine we push it to 1 solar mass. It doesn't make any sense to treat a population of 1 solar mass as a population of stars, because it's that's just not how the model works. So one of the things that we've been developing is a way to treat at least part of the population of stars as single objects or individual stars. And we have a pretty clever trick that we can use here, and it comes from the mass function or the mass distribution of a stellar population or population of stars. So if we look at this mass distribution, we can do this through like just measuring it observationally. We see that the distribution decreases very steeply with increasing mass. Basically, what that means is that the more massive stars are very rare compared to low mass stars. Just to give an example of how steep this is, if we take a typical population of stars, let's say we go from 1/10 of a solar mass, that's almost at the hydrogen burning limit, so that's kind of the lowest limit, and we go up to say 100 solar masses, and we take this mass distribution. The average mass of a star in this population is half a solar mass. So it's extremely, like the number of stars, or number of massive stars is extremely small compared to the low mass stars. And another very interesting thing about stars is that the amount of energy that they output increases enormously with their mass. So if you take something like a 10 solar mass star, the amount of energy that star outputs is much more than 10 times the energy outputted by the sun. It just increases an incredible amount.
So I assume they have a bigger effect on everything around them.
Much bigger. Like we have more massive stars, they output a lot more radiation. They tend to output very strong like winds, or this solar wind, for example, much more severe for more massive stars. And they can also go through processes like supernova explosions. So this deposits huge amounts of energy, and you can interact with your environment this way. So that's kind of the two kind of ingredients that makes up this clever trick that I'm going to explain. So we have very few very massive stars, but these stars are the stars that are the most important in terms of how they interact with their environments. So we take a model where we define some mass threshold. We say that stars below this mass threshold, we will just think of them as a population, and stars above this mass threshold, we will actually go in and we will think of these as single stars. And that is the model that we have been developing, and that has become very successful in the past, I would say, 5 or 6 years or so. So this now lets us basically model galaxies where individual stars are actually resolved objects in the simulations.
Okay, one deviation, just because I know I'm going to get crap from my geophysicist friend for not asking this question about computational power to get this done. I assume you're using some kind of supercluster of some sort. How many different CPUs are you running? Like 300 nodes with individual cores? Like, I just rough ballpark here. Put me in the ballpark so we can have some idea of like how many desktop computers are actually the equivalent of running on these programs at the same time.
So yeah, no, these are very expensive simulations. Like even with all these clever tricks, it takes a long time. Typically, one of my simulations, I have to run them around 1 million hours. So that's impossible on a single computer, right? So yeah, as you say, we split this into many different computers running in parallel. This is typically done on like up to a few thousand CPU cores or 1,000 computers, but it still takes us like a few weeks or maybe a few months to actually run these simulations. So it's a bit painstaking.
Yeah, I can imagine. It's also probably pretty nerve-wracking because yes, you're like, okay, it's just science. You can redo it, you can fail, but at the same time, the amount of cost and time, like you had to book time on the supercomputer, even if it doesn't cost your grant money specifically, you have to stand in line, and if it fails because you messed up a line of code to launch the program, I can imagine that would be so frustrating and nerve-wracking. It's probably up there almost with actually defending your dissertation when you hit go.
Yeah, I mean, for sure. And like one thing to be very careful with is to not start one of these simulations and then wait months and then look at it. Like we do look at the simulations as they are running. Like as
Yeah.
soon as I have a new output, I will go in and I'll make sure that like, does this actually make sense? Like, am I learning something or am I just wasting time?
Do you also like set an alarm so if it goes off at 3 a.m. you're up there looking at it right away?
No,
No.
that would never be possible. That makes
uh,
me miserable.
yeah, no doubt. Okay, well, one of the interesting things that I noticed about the paper was that it mentioned runaway stars and just generally like rogue stars roaming interstellar space. So I assume comes out of the fact that you can now look at these bigger stars as separate entities instead of populations. So what was the implication here?
Yeah, no, runaway stars is something that's fairly close to my heart. Like it's what I spend a lot of time on my PhD thesis thinking about. So basically, runaway stars, these are stars that travel at very high velocities. Typically, we say stars traveling at more than 30 kilometers per second is a runaway star. And these are very interesting because they basically come out from the star formation process when you get a cluster of stars. Like this cluster of stars will interact with each other, and sometimes they will actually kick each other, and some of these stars will escape at very high speeds. And we call these runaway stars. And these are very interesting because it gives us a way to take stars that formed in some location and let them travel very quickly to other places. So these are these rogue stars that just fly around. And that means that if we have some region of a galaxy, let's say we don't have a lot of gas there, like we have, at the very least, we have so little gas that we don't expect any star formation in this region. Then the first assumption that you would make is that there is probably no young stars here because we can't form stars here. But these runaway stars actually change that, because now you can form stars somewhere else and you can have these stars escape at high speeds and they can actually travel into these regions. So that means that we now have to think about, okay, even if we can't form stars in some location, we might still have young stars there. And that can cause interesting effects for the galaxy, also how we observe the galaxy. So this is a fascinating type of star.
I can imagine that would also potentially not mess up, but change how the mass comes together, like the distribution of the mass within the galaxy as it evolves.
Specifically the gas distribution, like the gas, that's kind of what the stars will affect mostly, like how because these are individual stars, they will not really affect any of the dynamics of the galaxy. They're just in terms of mass, they're negligible compared to the mass of the galaxy, right? But they do output energy, so they will affect how the gas behaves. And that's something that's quite important for how a galaxy evolves.
Okay, more parameters. One that I found kind of entertaining, mainly because I really didn't understand it the first time I read it, even in context, was stellar feedback. It came up in our back and forth as well as is in the papers themselves. Normally, when I think of feedback, I'm thinking of like a follow-on mechanism. To give two completely different examples, if I get angry and I mess up, and I'm more likely to mess up when I'm angry, I can fall into a feedback loop. I screw up, I get angry, I'm more likely to screw up. Or stereo feedback is a classic example where the mic picks up the sound from the speakers, which we're trying very hard to not do that here on the podcast, and it gets into a feedback from from the speakers back into the mic, back out to the speakers, back into the mic. So what is stellar feedback?
Yeah, no, that's it's a good question. I think, like, to start off, just saying, like, stellar feedback is ways for stars to interact with their environments after they've been formed. We can think of this as like stellar radiation that pushes on gas and also changes how the gas behaves. Stellar winds is another example of stellar feedback. Supernova explosions. So very generally, stellar feedback are processes that let star affect their surrounding gas. And we call this feedback because we're now letting stars change the environments that the stars are born out of. So it gives stars a way to regulate how they're formation happens. And this is where the term feedback comes from. Now, one distinction compared to your examples is that stellar feedback is a form of negative feedback, and your examples are examples of positive feedback. So positive feedback is basically when the resulting output strengthens the next input. So in your example with the microphone, we're now amplifying the sound, and then we're recording the amplified sound, amplifying it again, etc. So this is what this stereo feedback is. Now, for stellar feedback, it's actually the other way around, where the stellar feedback actually weakens the next star formation event. So if I give you like a real world example or analogy, we think of feedback in terms of like, let's imagine you have a sales pitch, like you have something that you're selling, and like how many sales you are doing will depend on the number of customers that you have. So if we assume that customers will only buy things that they don't already have, then that means that every time you make a sale, your number of customers will go down. So unless like if in case you sell something that never breaks or is consumed, then eventually you will run out of customers because everyone already have what you're trying to sell. That would be an example of negative feedback. And stellar feedback is more like that, at least generally speaking.
Okay, time for the dark side. The papers use the phrase low mass dark matter halo. And just recently we talked about gravitational lensing in a previous episode, and we did kind of talk about dark matter halos because it came up and I couldn't resist myself, even though I was pretty sure we were going to go here as well. So dark matter halos, I assume dwarf galaxies have them, and it automatically means that they're small too?
Yeah, that's true. Dwarf galaxies tend to have smaller dark matter halos. I don't think we should start a full discussion about what dark matter actually is, because that's probably an episode.
Yeah, we kind of did that as the two-part with Dr. Yorgos Fernaldo, so we can skip it for now. But I was just curious about if you're interested listeners, go back and listen to that. I know it's 2 hours altogether, so you might have trouble finding it, but it's an amazing discussion, so don't skip on it. But just in general, like, they must enter the simulation background somewhere with what you're doing as well, right? Like at some point that must be a parameter.
Yeah, for sure. No, there is, in the simulations we have a model that describes dark matter. So I can summarize it very, very simply. Like, so the reason why we have something that we call dark matter comes from the fact that when we observe galaxies, and we can measure their mass in two different ways. We can look at how stars move in this galaxy, and how they move will depend on the gravity between these stars. And that gives us a way to estimate the mass of the galaxy in a dynamical sense. So we get a dynamical estimate of the mass. We can also look at the galaxy and just, what is the mass that this thing have based on what I can see? So we can take all the mass of all the stars, we can take all the gas mass, and we can get another estimate for the mass, which is kind of a visual estimation of what the galaxy actually, what mass the galaxy actually has. And when we do this, we find a pretty big discrepancy. It turns out that the dynamical mass of galaxies is much, much higher than what we expect based on the things that we see. So to solve this problem, we introduce what we call dark matter, or that's just matter that we cannot see. So that's very simply why we have this dark matter, or why we need to have this dark matter in the first place. So what I assume, like, and from here on, like, now it becomes like up to the details of what kind of model you want to use for your dark matter model, for your dark matter. In my case, I work in a paradigm called the cold dark matter model. That means I basically assume that dark matter is some form of non-interacting particle that you cannot see visibly, and it's just there as an extra mass component. And this mass component is what we refer to as the dark matter halo. Now, if we measure many galaxies of different masses, and we estimate both this dynamical mass, or the halo mass, if you will, and we compare that to the stellar mass, we get what's called the halo mass stellar mass relation. And this is a relation that is actually positive. So smaller galaxies have smaller halos, and more massive galaxies have larger halos. This is a very well-established empirical relation. There is some interesting details. For example, when we look at dwarf galaxies, we tend to find that they have actually, if we just take this relation, assume that it's some linear relation, and we base that off galaxies that are around the Milky Way mass, a bit more massive, a bit less massive, and we take this to be linear, we actually find discrepancy for low mass galaxies. The stellar mass of dwarfs tend to be smaller than we expect them to be based on their halo mass. And one of the reasons for this is probably because these galaxies are more heavily affected by things like stellar feedback. But yeah, dark matter is definitely something that we do have to account for in the simulations.
Okay, so we've talked about dark matter, we've talked about number of stars, where you set a mass function as kind of like your starting assumption for your galaxy before you hit go on the simulation. Are there any other kind of like starting conditions we should know about?
I mean, yeah, we have the initial conditions for the simulation. So in my latest publication, when I simulated these dwarf galaxies, we picked dwarf galaxies because we were interested in these reionization relics, or this early star formation. And the way that we basically pick them is we use something like the cosmic microwave background to get some sense of what is the dark matter distribution at some point in the universe, very early on. And then we basically simulate this, how this distribution evolves, typically using only gravity and using only gravitational forces. This lets us simulate how these structures evolve throughout time. And then when we reach present day, we look at, okay, what kind of or dark matter halos do we have at present day? Is there anything that interests us in particular? And one key thing here, because we're running a cheaper model, we can run a very large volume. So we get a lot of examples of different halos that we can look at. And then we just select, okay, I'm interested in this particular one for whatever reason. I can then say, okay, what makes up this galaxy in my initial conditions, like where I started? I take this particular region and I say, okay, now I'm gonna put in all the gas, I'm gonna put in all the stars, I'm gonna use all my advanced models, and I'm gonna focus on this particular region. And this is what we call a zoom-in simulation. You're basically zooming in on a specific galaxy and how that forms. And this comes out of like the formation of structures in the early universe. And then we just evolve that thing with all the bells and whistles. And then when we reach present day, we can look at, okay, well, what was our expectations and how does it look in our simulation? And that lets us constrain all these models that we have.
All right, so the model, you called it Inferno. Great name, by the way. I don't know if you gave the name, but that's the name it has. And so with the parameters and everything else we've already talked about, you picked your individual galaxies to put into the simulation. So what do we better understand now about the formation of dwarf galaxies that we didn't know before?
No, we learned quite a lot. And actually on the topic of the Inferno name, maybe I should give a shout out here. So I picked the name for this model. I developed it in my PhD, and it's actually named after a pub that I frequented during my years as a PhD student.
It always comes back to beer.
Exactly. It's important part of doing research. No, but okay. So back to your question, what did we learn from this set of simulations of dwarf galaxies with this fairly advanced model? So we learned quite a lot. I think the things that especially interests me is considering stochasticity, or like randomness, as part of the galaxy formation process. Like now when we're dealing with individual stars, or like now stars are no longer a population, in this model, we're actually sampling this population. So instead of thinking of stars as things that have like average quantities, we're now looking at realizations of a distribution. And that means that this is inherently stochastic, right? So one of the things that we studied and quantified is like, how does this randomness that we have from the fact that the mass function of stars is somewhat random, how does this translate to uncertainty when we go out and observe one of these systems? And this uncertainty is something that we quantified. I'm also very interested in not just an uncertainty on our observations, but how does this randomness become randomness in feedback processes? And this is something that I'm currently working on trying to quantify. Another like interesting thing that we found is that so these galaxies that we simulated are very isolated and very low mass. But even these galaxies, they do form through like interactions with other galaxies. So you do have these merger, even if they're very small galaxies. And what happens for these systems is that you tend to build up at least part of the stars in your galaxies have a very like wide distribution, or like you have stars in very wide orbits. So you get this light profile when you look at the galaxy that is very extended. And this is something that we kind of expected for galaxies that are satellites to bigger ones, because then you can have interactions that make them basically puff up and become larger. But it wasn't as clear for these very isolated galaxies. So this is also something we find that I think is quite interesting.
Wow, you just answered the next question too, because I was going to ask about the shortcomings, and you've already given me all, and I was going to talk about how chaos theory and the outcome of any process is sensitive to the starting point as the flapping wings of a butterfly. But I think you summed it up perfectly, that the next step is to try to adhere to that natural complexity of galaxy formation and inputting some of these more random events into the simulation. But where do we go for the future? Do we just, in the near future, go to a bigger galaxy? Do we start trying to use machine learning to provide some of that randomness? Or are we going to go to quantum computing, because otherwise we just have no hope of actually doing these simulations? Could it even come to a rethink of the basic pillars of how we understand galaxy formation? So now you've got a crystal ball. Tell me the future.
Oh my God. Yeah, no, that's a very thing to do. I mean, when it comes to quantum computing, I can say immediately that I don't really have a good understanding of how that works. I don't think I can make any predictions. I guess generally when we see technological advances, we do also see like we learn a lot of stuff. So for sure it's going to help us in some way or another, but it's just very hard to say how. AI or like machine learning, I think, is more clear. Like that's something that we're already using in the astrophysics community. Like machine learning is a very good tool, especially for astronomy, where we're dealing with very, very large data sets. So that's like something that's being applied and is actually helping us making a lot of the things that we're doing much more efficient. I personally haven't really used any kind of AI or machine learning in my research, but for sure people are using this and thinking about it. I've even seen some example of people trying to use machine learning to speed up like galaxy formation simulations. So that's an interesting thing in itself. I think what I would add to like the future or like how simulations are evolving, one of the big recent changes that we've seen is this big uptake in the use of GPUs. This is a new type of hardware that is very good at making a lot of very small calculations extremely efficiently. So this is something that we're now working on, like adapting our galaxy simulations to work for these GPU, these new type of processors. And this is actually gonna speed up things quite a bit, I think. But it's still something that is in development. But when that becomes a thing, yeah, for sure, we're gonna be able to simulate larger systems, or at least in higher detail.
Okay, well, first off, thank you for being here, and we're Now on to the famous or infamous, depending on whether or not you like terrible science jokes. It's time for that traditional question where I ask you for your favorite or best, or in some cases, worst science joke.
All right, yeah. You prepped me for these questions. I've actually thought about it a little bit.
That's good, because the whole point is not to catch you off guard, because otherwise I'll get blank stares and like, oh my God, what did you just ask me?
Yeah. No, I have a joke that I find pretty amusing. I can't take credit for it. This is a joke I've heard several times in different contexts. But so here's my joke. A photon is at the airport and goes to print the boarding pass. At the desk, the receptionist asked, "Any checked luggage?" To which the photon replies, "No, I'm traveling light."
Perfect. Perfect. Well, hopefully it wasn't too painful, and thanks for being on Whimsical Wavelengths.
Thank you so much for having me.
Another episode to a close. You know the drill. If you haven't already, hit that subscribe button. Drop me a line on my social media. Send me an email. It's in the show notes. Give me some feedback. Give me some suggestions for another show. Or give me a question. Maybe if I get enough questions, I can do a Ask Me Anything. Remember, I am a volcanologist, geophysicist, so maybe you have questions, or maybe you just have questions that I can find a guest to try to answer. Whatever it is, if you have a friend who really needs some scientific escapism, you know who to suggest. In the meantime, I'll see you all in 2 weeks.
Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight. In a world so chaotic that misbehaves, melodies that echo show us six always. Colors intertwine, painting the sky. We're lost in the rhythm as the universe flies by. Oh, we're tuned in, feeling the beat of the unknown. Can you hear it? It's echoing through your bones. In this melodic maze we let